In our previous session, we have seen how to make field flux more sinusoidal, in this how to reduce harmonics in field flux. But anyway, in the field flux, harmonics will be there. Don't get scared of harmonics, just like non-sinusoidalness. Okay, so in field flux, we tried our level best to make better sinusoid. Okay, our non-sinusoidalness we tried to reduce in the field flux. And after that means let us think of induced voltage. Okay, even though field flux is having harmonics, or even though we have non-sinusoidalness in the field flux, let us try to make my induced voltage better sinusoid. Okay, actually here many things we can discuss, but this is machine simplified, means that you should be able to crack your GATE 2020. So I don't want to discuss each and every concepts in detail. Okay, now let us think of distribution of the winding. Okay, if I want to distribute the winding, means that, for example, this is the stator. Okay, in stator, if I keep A here, I am going to keep A dash here, and B here, B dash here, and C here, C dash here. Okay, such that two poles will be formed. For example, from the field point of view, two poles are formed. Okay, two poles are formed, and this pole flux is not sinusoidal, it is having harmonic component. So even though you have field flux harmonics, how to reduce induced voltage, harmonics in induced voltage, or how to improve sinusoidalness. Okay, I don't want to prove now, because basically our textbooks and all, most of the textbooks and most of the faculties also, they will try to prove because of distribution how voltages are becoming more sinusoidal, or how harmonics are getting reduced in induced voltage. They will try to prove from formula. No, we should not prove from formula. Rather than that, we have to analyze. Okay, so we will analyze maybe in the detailed course. For time being, I'm not going to analyze. Now see here, for example, if I have 1, 2, 3, 4, 5, 6, if I have only 6 slots, I can keep all the conductors of A dash here, I can keep all the conductors of B dash here, I can keep all the conductors of C dash here. But I normally don't have 6 slots only, I'll have very number of slots. For example, okay, so under one pole, how many slots are there now? This is going to be one pole area. Under one pole area, 1, 2, 3, 4, 5, 6, 7, 8, 9 slots are there. Under that conditions, under one pole, all 3 phases will be there or not? Yes, because A phase per pole, this is the point of pole, per pole area, A winding will be there, B winding will be there, C winding also will be there. Okay, now rather than keeping all A conductors here only, let me distribute the winding in 3 slots. So these 3 slots is going to be for A, these 3 slots is going to be for A dash, such that, for example, A1 dash, A2 dash, A3 dash. Okay, such that, see here, A1 conductor, from here A1 conductor, back to back connection 1 dash, again A2 2 dash, again A3 3 dash. So 1 dash, 2 dash, 3 dash, all conductors are connected in series. Okay, all turns are connected in series. Similarly, for B, let me take this. For C, let me take these 3 slots. This is called as distribution of winding. Rather than keeping all the turns in one winding or one slot, let us distribute the winding. Because of distribution of the winding, harmonics will be reduced. Okay, I will not be able to analyze now, because unnecessarily it's a time waste. Okay, so see here, if I distribute the winding, harmonics are going to be reduced. But see here, harmonics are reduced fine, but net induced voltage also will be reduced. RMS voltage will be reduced. So if I keep all these 3 conductors in one slot only, okay, if I keep all these 3 conductors, slots are there, no? In each slot conductors will be there, no? If I keep all these slots in a single, all these conductors in a single slot, okay, then induced voltage will be more. Because of the distribution, induced voltage will be less. If induced voltage is less, actually ideally we should not say induced voltage is less, because given voltage, rated voltage is constant. For example, rated voltage is 11 kV. In order to produce 11 kV, because of the distribution of the winding, net voltage is getting reduced, means that you have to provide more number of turns in order to reach 11 kV. Okay, so we should not say, like, in practice, from practical point of view, we should not say means because of distribution net voltage is reduced, is wrong. But we can say because of distribution, number of turns of copper will be increased in order to meet the same rated voltage of 11 kV. Okay, so number of turns has to be increased, means that volume of copper requirement will be increased. Okay, so we have to invest more, it's fine. Even though, like, we are ready to invest more amount of money in order to attain sinusoid. So getting sinusoidal voltage in alternator is not that much simple. Okay, we have to invest huge amount of money to make induced voltage more sinusoidal, but it's okay, we are going to invest because our biggest customer is induction motor. Okay, so see here, because of the distribution of the winding, voltages will be reduced. That reduction factor is called as distribution factor. Okay, so that distribution factor KD is going to be sine Q gamma by 2 by Q sine gamma by 2. It is the derivation for fundamental. Okay, I'll explain, just wait. Okay, what is Q here? What is Q here? Q is called as slots per pole per phase. In the sense, per pole per phase, how many slots are available for the distribution of the winding is going to be called as Q. Okay, for example, see here, per pole, under one pole, how many slots are there? Per pole, how many slots are there? 9. Okay, out of 9 slots, all 3 phases should be there or not? Yes. So 3 phases should be there, in the sense, under one pole, all phases should be there. Under one pole, how many slots are there? 9 slots are there. 9 slots divided by 3 per phase is going to be 3. So these 3 slots are available per pole for the distribution of the winding or not? Yes. So Q, slots per pole per phase, is nothing but how many slots are available per pole per phase for the distribution of the winding. Distribution of the winding is going to be this. Okay. Now second thing is, like, what is gamma? Gamma is nothing but the slot angle. Okay, so what is slot angle? Slot angle is this. Okay, angle between slot to adjacent slot is called as slot angle gamma. Okay, so gamma is called as slot angle. Okay, so everything will be in electrical terms only, dear. Electrical terms only, not mechanical terms. Like, electrical to mechanical, it's a very simple thing. We can discuss in DC in detail. But anyway, let us see here. For example, if I have one conductor here, okay, if I have 2 poles here, okay, so this is the rotor. If I rotate this in this direction, as of now, induced voltage is 0. Now, if I rotate this by 1 revolution, 0, positive max, 0, negative max, 0. So, if I revolve this 1 revolution, how many cycles of induced voltage will come? 1 cycle. 1 revolution, 1 cycle. Okay. So, in electrical terms, induced voltage here is going to be, for 1 revolution, this much will come. Induced voltage. Okay. So, this is the thing. For example, if I think of 4 poles, N, S, N, S. Okay, so as of now it is rotating like this. As of now it is negative maximum. After 90 degrees it will become positive maximum. After 90 degrees it will become negative maximum. After 90 degrees it will become positive maximum. So in this case my induced voltage is going to be, as of now, negative maximum 0, positive maximum 0, negative maximum 0, positive maximum 0, negative maximum. Okay, because see here, as of now it is negative maximum under S pole. Negative maximum, for example, means if I rotate this 1 revolution, negative maximum, positive maximum, negative maximum, positive maximum, negative maximum. Okay, so if I revolve this 1 revolution means that 2 cycles will be generated or not? Yes. So electrically speaking, what is meant by 2 cycles? 2 cycles distance electrically, 2 into 360 degrees. Okay, 1 cycle is 360. So if I rotate this mechanically 360 degrees, electrically how many cycles will be the induced? 2 into 360. Okay, so what is electrical angle here? Theta electrical equal to P by 2 into theta mechanical. Okay, so mechanically if I rotate this by 90 degrees, electrically what is happening? Negative maximum to positive maximum, negative maximum to positive maximum is going to be 180 degrees. So 4 poles, 4 divided by 2, 2 into mechanical is going to be electrical. If I rotate this 360 degrees, it is going to give you 2 into 360 degrees, 4 by 2. Okay, forget about this. Now slot angle, everything is going to be in electrical terms only. Okay, electrical angle only. This is called as slot angle. Okay, so my means induced voltage will be there. In future we are going to write it down, induced voltage without distribution, but because of distribution my induced voltage will be reduced. Okay, now let us think of for higher order harmonics. For example, if I have sinusoid, actually though I am covering a few things, it doesn't mean that I don't know. In future, in detailed course, I will touch each and everything, and immediately after GATE exam, I will launch, I think, GATE, interview sessions. Okay, so very important questions of interview sessions I will discuss separately, but let me target GATE 2020 first. Okay, for example, third harmonic. Okay, so fundamental, if it is rotated by 180 degrees, third harmonic will be 3 times 180 degrees. 3 times 180 degrees. Now let me start from here and let me go by slot angle gamma. Okay, so with respect to black it is going to be gamma, but with respect to red it is going to be 3 gamma, no? Because by the time in black, if I travel for 180 degrees, in red means 3 into 180 degrees, because half cycle 180, again half cycle 180. Okay, so with respect to black, if I move gamma, slot angle gamma, with respect to triplet harmonic, it will become 3 gamma. Okay, now let us see here what is distribution factor for third harmonic or any harmonic component H. So KD for H harmonic component is going to be sin Q gamma slot angle. That particular slot angle will become H gamma by 2 slot angle divided by Q sin H gamma by 2. This has to be remembered. Of course, we will solve multiple problems such that automatically you will understand the importance of this formula. Okay, now next thing here is what is Q gamma. Okay, what is Q gamma? See, what is Q? Slots per pole per phase. So total number of slots per pole per phase it became 3. Okay, so total slots per pole per phase is going to be Q. So is going to be 3 slots multiplied by slot angle from here to here plus angle from here to here plus angle from here to here is going to give you phase spread or not. Okay, so let me repeat it again. Total number of slots per pole I got 9 slots. Per phase I got 3 slots. 3 slots multiplied by slot angle will give you phase spread. This is sigma phase spread. Okay, now Q gamma, if it is phase spread, how to write this equation again? Okay, so let us think of KD, maybe actually 1 is going to be sin Q gamma by 2 by Q sin gamma by 2. Okay, now from mathematics point of view, sin theta can be approximated to theta if and only if this theta should be very small and theta should be in radians. This is important, radians. Anyway, in solving the problems we will see. Okay, so slot angle is going to be less only. Slot angle by 2 is going to be less only, but it has to be written in radians. In solving problems we will see. So this is going to be sin q gamma by 2 by sin gamma by 2 is nothing but gamma by 2 only, approximated, because this is less and that particular angle should be in radians. So this is going to be q gamma by 2. Now what is q gamma? Very simple, out of total number of slots per pole, per phase. So slots per pole, per phase. Okay, so these many number of slots multiplied by slot angle will give you the phase spread. So this equation will become sin sigma by 2, phase spread by 2 by sigma by 2. Okay, and one more thing is fractional slot will come. Okay, how to calculate q? Means till now in old gate only one time they asked, but anyway, means if it is fractional slot, for example, q, what is q? Slots per pole per phase. Okay, if slots per pole per phase is integer, integral slot winding. If it is a fraction, fractional slot winding. Okay, for example, in the example taken, how many slots per pole per phase? 3. Means that total number of slots are 18, per pole 9, per phase 3. Okay, so that is integral slot winding, because slots per pole per phase is integer. So if it is integer, integral slot winding, okay. Now if it is like fraction, okay, if it is fraction, this is called as fractional slot winding. Fractional slot winding. Okay, normally in practice we use fractional slot winding only, we never use integral slot winding. Of course in our problems, like in exam and all, integral slot winding may come, but in practice means we have to use fractional slot winding only, because some vernier torques will be there, electromagnetic interference will be there, harmonics will be there. Those I will keep it for detailed machine analysis. But how to find slot to harmonics, we are going to take a problem very soon. Okay, how to calculate, I'll tell you. How it is coming, maybe in the detailed machine analysis, definitely I'll come to know. You will come to know. Now, if it is fraction slot winding, for example, if fraction is 7, 3.5. Okay, if it is 3.5, means what we have to do is we have to write 7 by 2. Okay, if it is 7 by 2, that 7 should be considered as q. Okay, means that, again let me repeat, in fractional slot, for example, if you get 3.5 can be rewritten as 7 by 2. In the sense, basically if it is 3.5 slots for phase A, 3.5 slots for phase B, 3.5 slots for phase C, we cannot allocate. Okay, so in that way, means we are going to follow actually in the design of winding. Maybe in the detailed course for sure I'll tell you about the vernier torques, and I'll tell you how that electromagnetic interference, if you use for example integral slot winding, you cannot use your mobile phone also adjacent to your alternator. Okay, such a huge EMI will come, your ammeter, voltmeter, nothing will work. Electromagnetic interference will be severely high. Now in fractional slot winding, that particular vernier torques or electromagnetic interference can be reduced. Anyway, in place of 3.5 if you get, please write in P by Q form or X by Y form, and the numerator you please take it as Q. Okay, in solving the problems we will discuss again all this.